Hi guys, hope you are doing well. I've already started a video on ionization energy and the factors affecting ionization energy. Thanks for watching my video. In my previous video, I have explained what is meant by the term ionization energy and how those factors alter ionization energy. I've already discussed atomic radius, which is nothing but the distance between the nucleus and the outer shell electron, and affect how this will affect ionization energy we will see. So the nuclear charge, very quickly, atomic radius down the group, what happened to the atomic radius down the group, and at when we move down the group in the periodic table, and atomic radius when we move across the periodic table, what happened. So atomic size increases down the group, atomic size or radius, same thing, increases down the group. Down the group due to increase in number of shells, due to increase in number of shells. When you look at the trends of atomic radius, or all of them, first atomic radius stays the same when we move across the period. I've already discussed this point in my previous video. Now nuclear charge. Look at the nuclear charge. Nuclear charge. It is the force of attraction between the nucleus, this is the nucleus, and the electrons in the outer shell. One more time: lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, neon. 3 electron, 4 electron, 5 electron, 6 electron, 7 electron, 8 electron, 9 electron, and 10 electron. All these electrons are placed in the same shell. Sir, we didn't get it. No problem. See, 1s2, 2s1, 2s2, 2s2, 2p1. 1s2 is common. 2s2, 2p2. P has 3 orbitals, so we can accommodate 6 electrons. 2p, 2p2, 2p3, 2p4, 2p5, 2p6. 2s2 also common. 1s2, 2s2 common. So it has 2 shells. When you move across the periodic table, and this is the second period, this is the second one, it has only 2 shells. That's why they are placed in second period. As you move across the periodic table, the number of the electrons increases and they are present in the same shell. So we have more and more electron as you go across the period. The more and more electron mean more and more force of attraction on the outer shell electron. Mean nuclear charge increases as we move across the period, because all the electrons come close towards the nucleus. Look at the nuclear charge. Some teacher use the average nuclear charge. I don't want to use the average nuclear charge. See, this is the nuclear charge, force of attraction between the nucleus and the outer electron, and more electron coming towards the second shell. So more and more nuclear charge increases as we move across the period. Okay, so nuclear charge has no effect when we move down the group because the number of shell increases. So I want to write here nuclear charge increases across the period. Look at that. Increases across the period. What happened to the nuclear charge? Nuclear charge. Nuclear charge increases across the period. Meaning, the size decreases, nuclear charge increases. Nuclear charge down the group. Look, lithium, sodium, potassium, rubidium, cesium, francium. Francium is the biggest, in terms of the size, it has the biggest size in the periodic table. It has 7 shell. So 1, 2, look at the 7 shell. 1, 2, 3, 4, 5, 6, 7. These, look at the outer shell electron. Look at the electron. Look at that. These electrons. So what happened to the force of attraction here to here, here to here, here to here? It diminishes, it decreases, or it has no effect. So we are not considering the factor of nuclear charge when we move down the group. Nuclear charge is the good factor when we move across the period, not down the group. In the same way, when you go down the group, atomic size, atomic radius increases. So when we move down, now shielding effect, or it is also called screening effect. Both are same, shielding and screening. So we will first see the trends of the shielding effect down the group and across the period. And look what happened when we move down the group. Lithium, sodium, potassium, rubidium, cesium, francium. Hydrogen, first shell, so first period 1, period 2, period 3, period 4, 5, 6, 7. 7 shell. So look at it has 2 shell. Look at this has 6 shell and 7th shell. Mostly shielding effect show a prominent effect when we have more than 4 shell. Not for 1, 2, 3, but we can consider shielding effect also. But you can see the effect of the shielding on the ionization energy when we have 4 or more than 4 shell. Suppose that's my nucleus. 1, 2, 3, 4 electrons, 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 electrons. Okay. So when these electrons are present away from the nucleus, they have less force of attraction. Less force of attraction. Less force of attraction. These electrons are called interweaving electron. Hinder the effect of nuclear charge, or the force of attraction between this nucleus and the outer shell electron. You have less force of attraction. See, as the electrons go away from the nucleus, the force of attraction decreases. Force decreases. Force of attraction decreases due to the presence of all these electrons, interweaving electron. Suppose we assume these are the barriers. So more the barrier, less will be the force of attraction. This is called shielding effect. More protection, more layer. Like during the winter season, we normally wear more layers. So these electrons act as a barrier, and which prevents the force of attraction between the nucleus and the outer shell electron. That's called the shielding effect. And shielding effect is more prominent when we have more than 4 number of shells. So as you go down the group, what happened to the shielding effect? Obviously it increases. So shielding effect down the group increases shielding effect. Shielding shielding effect down the group increases. Shielding effect down the group increases. More shielding when you go down the group. Shielding effect down the group increases. And when you go across the period, shielding effect stays the same because the size stays the same. Across the period, shielding effect across the period, shielding across the period. Across the period stays same. It stays same. Why? Because there is no change in the size. Size stays the same. So how all these three factors or variable affects the ionization energy? First, we will see what happened to the ionization energy when we go down the group and how these atomic radius increase or decrease ionization energy. Okay. First factor, atomic radius. And we know that atomic radius increases down the group. So how this will alter ionization energy? Atomic radius increases. So I'm using these group 1 element. Atomic radius, we know that atomic radius increases down the group. It is the amount of the energy needed to remove the electron. Okay. What happens when we move down the group? Atomic radius increases. Size become bigger. Look at the size. Size become bigger. Electron, 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 electron. So this electron can be easily removed by using less ionization energy because this is away from the nucleus. As the electrons move further away from the nucleus, it needs less amount of the energy to take away. So ionization energy decreases down the group due to increase in atomic radius because we need less amount of the energy to take away this electron. So as we move down the group of periodic table IE, ionization energy decreases due to increase in atomic radius. Why atomic radius increases? Due to increase in number of shell. I want to highlight these points. Ionization energy decreases down the group due to increase in atomic radius. Meaning, to remove these electrons, we have to give a small amount of energy compared to these two electrons. They need more energy because of the force of attraction. So ionization energy decreases down the group. Now, so what's the relationship between ionization energy and atomic radius? What's the relationship? Now, ionization energy, IE value, decreases down the group. So what happened to the ionization energy across the period? I'm repeating my words. These are called trends, and these trends repeating in the periodic table at the regular interval of the time. Now, we have seen the factor how this atomic radius alter ionization energy. Now, the next one, ionization energy across the period. When you explain ionization energy across the period, you have to focus on nuclear charge because these two factors are not providing any change in the ionization energy. Now, across the period, lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, Fe is iron, my bad, fluorine and neon. Neon has the highest one. 3, 4 number of electron, 5, 6, 7, 8, 9, 10. When we go across the period, atomic radius stays the same. So I'm not considering atomic radius. What happened to the nuclear charge? Guys, nuclear charge increases because of moving of the electron, pushing of the electron towards the nucleus. These elements have same number of shell. First of all, the main energy level is 2. First energy level and second energy level. But it has 3 electrons. Look at that. To that second energy level, it has 2 plus 1, 2 plus 1, and 2 plus 2, 2 plus 2, 2 plus 3, 2 plus 2 plus 4. First energy level 2, 1 extra, one more extra electron. So as you move across the period, the number of shells are same, but the total number of the electron increases, and they try to move towards the nucleus. That increases nuclear charge. Mean we have one extra solid force. That extra solid force is called nuclear charge. Because of the nuclear charge, these electrons are forcefully and strongly bonded to nucleus. And this factor, the ionization energy is the amount of the energy needed to take away the electron. First of all, they are holding tightly with the nucleus. So what do you think? What is your guess? When we move down the group, nuclear charge or a force of attraction between the nucleus and the outer shell electron increases. First of all, that ionization energy has to break this nuclear charge, and then it is available to take off the electron. So when the nuclear charge increases, ionization energy also increases. It's a strong bond. We have to take away the electron. This electron, first to break down this bond, nuclear charge, that's the force of attraction between this electron and that one. We have to break down some amount of the energy utilized to break down this. Then we can remove this electron. So to remove the electron from outer shell across the period, we need a lot of energy because of this force of attraction. This is kind of a barrier which we have to take off to remove this electron, outer shell electron. So in a nutshell, we can say as we go across the period, nuclear charge increases, which also increases ionization energy. So nuclear charge and ionization energy are very friendly. Mean I'm giving you one relation, like nuclear charge NC is directly proportional to IE. Both are friends. One increase, another also increase. If one decrease, another also decreases. So what's the relationship, guys? This is the happy face of nuclear charge. I have the nuclear charge 1, that one. I have nuclear charge 1 with a happy face, and I have ionization energy, which is also a happy face. Both are friends. And IE increases due to increase in nuclear charge. So what happened to the ionization energy when we move across the period? Across the period, nuclear charges increases, so ionization energy increases. Meaning it is hard to take away the electron from the neon. Outer shell is completely filled. Now, the last factor is how the shielding effect alter the ionization energy when we move down the group. I want to stop my video here. I will come back and I will explain the next factor in my next video. And after that, we have to do the successive ionization energy. Meaning, if you take away the one electron from any element, can we take away one more electron? Or whether this energy stays same when we are going to take away electrons. So that we will see in my next video. Thank you so much, and please keep on watching my videos.